So far, in the previous lectures, we have seen the design of shaft based on strength. So in this lecture, we are going to discuss about the design of shaft based on rigidity. So in shaft design, in some of the cases, we should design the shaft based on the angle of twist. Okay. So the need for designing the shaft based on angle of twist is, in some of the cases, the angle of twist will be high. Okay. So if the angle of twist is high, then that will affect the rigidity of the system. Okay. So in such cases, we have to focus on the design of shaft based on rigidity, and we have to keep the angle of twist within safe limits. Okay, so the torsion equation is mt by j is equal to g theta by l, and we know that mt is the torque and j is the polar moment of inertia. For a circular section, the polar moment of inertia is pi by 32 d power 4. Then g is the modulus of rigidity, so it's a material property in Newton per mm square. Theta is the angle of twist. We have to substitute the value of angle of twist in radian. And L is the length of the shaft subjected to twisting moment. Okay. So in this, in the strength design, we will consider some allowable shear values, and we will calculate the shear value and we will compare it with the allowable values, or otherwise we will substitute the allowable shear value and we will calculate the diameter. So similarly, in the case of rigidity based design, we have to consider some allowable angle of twist values. So after substituting the angle of twist value, then we can calculate the diameter to keep the rigidity within safe limits. So I am going to solve a simple problem on that. A solid circular shaft is to transmit 112 kilowatt. The power is given, it is 112 kilowatt at 500 rpm with the provision for 20% overload. So we know that 20% overload means the T maximum is equal to 1.2 times of the T mean, that is mean torque. Then the angle of twist must not exceed 1 degree. So the angle theta is equal to 1 degree. We can convert it into radian. So 1 into pi by 180, you will get pi by 180 radian in a length of 15 diameters. Okay. So the considered length is 15 times the diameter. Okay. So the meaning for this statement is the allowable angle of twist is 1 degree for a length of 15 times the diameter. Okay. So we have to focus on only this region. So consider L is equal to 15 times the diameter. Design the shaft. Adopt mild steel with a working shear stress of 60 megapascal. So the tau allowable is given, but anyway in the problem we are not going to use the tau allowable value, because in the problem the angle of twist is given, so we can design based on the angle of twist. So if in the problem the angle of twist value is given, then you can design the problem shaft by using the torsion equation. Okay. Further, if you want to compare your solution, then you can calculate the diameter based on the strength, that is by using the tau, and you can take the maximum value. Okay, so the torsion equation is mt by j is equal to g theta by l. The power is given, it is 112 into 10 power 3, and the power equation is 2 pi n mt divided by 60. Okay, so the n is given, it is 500 rpm. So actually here it is 500 rpm. Okay, into mt. So mt is equal to 2139 into 10 power 3 Newton mm. Okay. So further we can substitute the mt value in this equation, and j is pi by 32 d power 4. So substitute the value of j, g. So g is the material property, and for mild steel the modulus of rigidity, that is g, is equal to 8 into 10 power 4 Newton per mm square. So we can substitute it, and theta we can substitute it, it is given, then L is equal to 15 times the diameter. So if you solve this equation, finally you will get D is equal to 65.5 mm. Further, by using the R20 series, we can calculate the standard diameter, that is 71 mm. Okay. So this is the design of shaft based on rigidity. Next topic is whirling speed of shaft. Okay, so it is, or otherwise we can call it as critical speed. So in dynamics, you must have studied about the resonance. So resonance means when the external frequency or the forced frequency of the system matches with the natural frequency of the system, then the system will vibrate with high amplitude. So that state is called as resonance. So in case of rotors, the resonance speed is also called as whirling speed. Okay, so before designing any shaft, we must calculate the whirling speed of the shaft. At least based on the degrees of freedom, we will have the number of whirling speeds. For example, if a system has 5 degrees of freedom, then it will have 5 natural frequencies. So minimum we should calculate the first 2 natural frequency, and remember that the operating speed of the shaft should not match with the calculated whirling speed. For example, if the initial whirling speed is 100 hertz and the second natural frequency is 200 hertz, then we should not operate the shaft in 100 rpm, 100 hertz or 200 hertz. Okay, the operating speed of the shaft should not match with the whirling speed, because if it matches, then what will happen is the amplitude will be very high. So for linear vibration, we will generally calculate the natural frequency by root of 1 by 2 by root of k by m. There k is the stiffness and m is the mass. But in the case of rotors, we can calculate by using Fn is equal to 1 by 2 by root of g by del. So g is the gravity and del is the deflection. So for beams, we know how to calculate the deflection. So we can calculate the deflection, and here the g value is substituted. So we can, if you want to calculate the natural frequency of the system, then you can calculate the del, you can substitute it, and you can calculate the natural frequency. Okay. So in the case of 2 to 3 loads or 2 to 3 deflection, then we must use the Dunkerley's method for calculating the natural frequency. But anyway, the important thing is the operating frequency of the shaft should not match with the whirling speed of the shaft.